everyone. Welcome to our presentation, which is on the online memory leak detection in the cloud-based infrastructure. I am Anshul Jindal. I am currently a third-year PhD student at Technical University of Munich, and this work was done with the Huawei Munich Research Center. So I'll start with the outline of my presentation, which starts with a bit of an introduction towards memory leak, but I think everyone already knows what a memory leak is. Then I'll move towards the goals which we wanted to achieve as part of this work. Then how did we achieve those goals? So I'll give you the implementation, the methodology, the approach which we developed as part of this work. Then show some results like how our algorithm, the developed approach worked on the results on the data set. And finally, some conclusion and the future work, which where this work can be extended to. So I'll start with a bit of an introduction, like what is a memory leak. So as everyone already knows, a memory leak is a loss of a memory when a programmer fails to return the memory and which it has you obtained for a temporary use. So usually this is how the memory utilization pattern in the memory leaks looks like, where you have with where the memory utilization is increasing as the time progresses, and after a certain time it would reach 200% memory utilization. So this can be regarded as a potential memory leak case, but it is not generally always that this is a memory leak case, because the application can also use some memory utilization in a linearly increasing fashion as well. So now what is a memory leaks on in a virtual machines in the cloud? So there are some long running software services on the cloud which are susceptible to memory leaks. So if they start to use a memory and then they don't clean it up, so then the memory is still there, memory use is still there, the objects, then which can cause towards a memory leak actually. So what are these effects on the virtual machines in the cloud, which they compromise the performance and the stability of the services or the application if such a memory leak is there. And this compromisation of the performance can lead to the catastrophic impact on the critical infrastructure. So if we have some critical infrastructure, then that if such a memory leak can lead to a catastrophic impact. And usually you require a restart on the virtual machines if such a memory leak is detected, and then this involves a downtime of the applications which you don't want to have in the applications which are used for critical infrastructure. So what are some challenges on the virtual machines in the cloud? They are like hard to trace actually during development due to this new development architecture, application development architecture of microservices, where different teams are working on different particular microservices of an application, and until unless they are combined together, so one cannot actually understand whether there is a memory leak or not. And the applications are written in a diverse programming languages. So a tool developed for a certain language might not work for another language. So one has to develop the tools for all the programming language to detect a memory leak. And they are very hard to monitor on thousands of virtual machines running in the cloud. So if a particular administrator has to look through the memory utilization of all those machines and interpret them as a memory leak, then it would feasibly not possible. Yeah, and for lastly, if there is a particular application, if you want to analyze using some static code analysis, then they require some code modifications, and which generally adds to the performance overhead of the application. Yeah, so this is just a bit introduction towards memory leaks on the virtual machine in the cloud. And before proceeding into the implementation, we did some initial research on like how the memory leak patterns of nowadays applications look like. So we deployed some application and monitored their memory usage. Those applications were having memory leaks. And we saw that they can be classified into two patterns. One is a linearly increasing pattern where you can see the memory utilization is linearly increasing. If so this can increase without a noise, or this can also increase with noise over here. The second pattern is a sawtooth pattern where we see the memory utilization increase and goes down, increase and goes down like a sawtooth. And if we zoom inside this particular pattern over here, actually we can see that there is a this trend you would see actually where it generally increases and goes down, increases and goes down. So this is quite a general trend in a memory leak actually. So yeah, so these are some basic introduction towards the memory leak. So now I'll go towards how we approach this problem of memory leak detection on the virtual machines in the cloud. Uh, Before going into the approach, so let's see what are the goals which we wanted to achieve as part of this work. So one of the major goal was to the detection of memory leaks on these virtual machines without any inside knowledge of how the applications or what applications are running or in which programming languages they are written into. The second major goal is to have this implementation a minimal effect or minimal overhead on the application, and the detection should be in a reasonable time. And lastly, the develop approach should be scalable enough to scale to thousands of virtual machines. So yeah, so these are our three major goals as part of this work. So now let's see how we approach this problem with the methodology. So we saw that the memory leak trends have like on the, if we go from the back end side towards the front, we will always saw a linearly increasing pattern over here, as you can see in this diagram over here. So what we did was we try to fit a line from the back side of a particular time series, which we also called as a linear backward regression, that we try to fit a line from the backside on this particular trend. And to where to stop actually would depend. So we initially started with we initially before doing this trend detection of the trends, we put these points which we call as a change points on this time series. So we use change points algorithm to detect change points where there is a significant change happening in the metric time series over here. And so now we fit a particular line from one change point to another change point. So all the points in between those two change points, so a line would be fitted on top of that. And if the line is a good fit based on the R2 score, and if we extend the trend line to a certain time and it reaches a particular threshold within this critical time, and so if the time where this particular trend is reaching this threshold within less than the critical time, then we classify this window of two change points as an anomalous window over here. So there are some, so this is some basic part. So there are some other stuff as well, like if you have if you have to fit lines for different window sizes. So we pick the best and the longest one, as you can see in this diagram over here. So there are change points and there are these two lines fitted on this top over here, and we pick the good fit, which is based on our R-square score over here. And this is not a good fit, so we discard that part. And this again can be extended towards many window sizes and many trends lines actually. So over here it's two, and it can be extended to multiple windows and the trend lines. So now, so this methodology we added into an algorithm which we called as a Precog, which means to recognize what will happen in the future. So as part of this algorithm, we input a memory utilization time series data, which consists of a timestamps and the memory utilization of a virtual machine. This is passed into a pre-processing module, which removes some of the noise and averages it out for a certain time interval. After doing pre-processing, we may use this as a training data and we pass it into trend lines fitting module, as we saw in the previous slide, where we detect different trends. So after detecting these trends, we want to have good trends. So we pass this into a detect trends module where we have the two another major inputs, which is the minimum R2 score and R square score and the critical time. So based in these two parameters, we classify these trend lines over here, whether they are good trends or whether we should keep them or not. So after running this, after passing these trend lines through these detect trends, we get some of the training trends based on these two major parameters over here. And these training trends are saved into the file system. So these training trends usually have, so by saving all the trends, we mean that we save the training trend slope, the duration, and from when to when those trends appear in the training data. So there is a bigger assumption over here that in the training there is a no memory leak. So we assume all the training trends are the normal usage of the application. And along with saving all the trend, we also save the maximum slope among all the trends and the maximum duration as well among the trends. This is just to enhance the add an optimization to the algorithm. So after saving these training trends, we get a new data, so which we want to analyze whether to see whether this new data has a potential memory leak case or not. So again, this new data is passed into the training lines fitting module, which detects the trends, trend lines, and it is passed into the detect trends module. And then based on that R square score and the critical time C, we detect the new trends. And these new trends are then compared with the training trends to see whether these new data trends are bigger than the training trends. By bigger, I mean that they have a higher slope and a longer duration, so that we can classify these new data trends as a memory leak trends or not. If they are bigger than the training trend, we then say that these new data trends are memory leak trends. And this results into those particular trends window to be anomalous. This whole part over here is part of an Precog algorithm. We ran the experiment on the 4 physical core machine with Intel I Core 7 with hyper-threading enabled and 16 GB of RAM. So now so this machine was used for running the test, and the test was on the two dataset. One was from the real cloud virtual machine dataset provided by Huawei, which has total 60 virtual machines dataset with 20 as memory leaks and 40 without memory leaks. So this high number is because we ran specifically memory leaks application on those virtual machines. And then on the synthetic data set, we manually generated some synthetic data set, which had 90 of those has memory leaks and 90 of doesn't have a memory leak. So now let's see some of the results on this data set. So over here, you can see a linearly increasing pattern of memory utilization. So on the x-axis is the unit time and the y-axis represents the memory utilization over time. And then there are three things as part of this figure. So one are the change points. So these change points are represented in the training data. And the last change point represents the end of the training data. And on these change points or within these change points, there are these training trends, which are represented by red line, red dotted line. And lastly, the algorithm was able to classify this window over here as an anomalous window because it sees that this testing window has a higher trend as compared to the training time. So similarly, we ran the algorithm on the sawtooth pattern where this multiple training trends were detected and the algorithm classified the last test window as an anomalous over here. And the third case is where the test that has a linearly increasing pattern, but in the training we were not able to find any training trend. So this was not detected as a training trend because this doesn't have a higher memory utilization. It is only from 32 to 34 utilization. And but still the algorithm was good enough to detect this particular window as a memory leak trend. And lastly, I'll show you case where the testing trend is quite similar to the training trend. And in the training, the algorithm was able to detect the trends, and the algorithm saw that in the testing as well, this trend is very similar to the training trend. So it didn't classify this particular use case as a this particular case as a memory leak, which was correct as part of the thing. So yeah, so these are some of the cases where they just show you how the memory leak, the precog works. So to summarize this algorithm results, I show you the F1 score on the synthetic and the real data set. So we have the synthetic further classified into linearly increasing or with noise and without noise and the sawtooth pattern. But overall, so in the synthetic, the algorithm was able to achieve a 90%, 0.9 of F1 score and 0.857 on the real cloud dataset. Yeah, so these were some of the accuracy scores on the dataset. Now we want to evaluate the algorithm, like how much time does it take for the training and the prediction. So in the training time, we saw that if we keep on increasing the number of time ticks, so the algorithm was able to scale it linearly over the time. But the training time is not that useful in the in the real scenario. The main is the prediction time. So we saw that the prediction time was done within 1 second for even for 100,000 time ticks, which is quite good actually, and it scales linearly with the number of time ticks over here. And lastly, we want to evaluate this algorithm based on how sensitive it is towards the parameters. So we use two of the parameters. One is the minimum R square score, and the other is the critical time. So if we saw from 0.5 to 0.95, like how this algorithm showcase the accuracy, we saw that after a certain time, certain R square score of like 0.85 or 0.9, the algorithm becomes quite strict, that it will detect those very strict trends actually in the training data, and it was not good enough. So that's why we put the R square score as 0.8. And similarly with the critical time, where it's mostly dependent on how the data set is and what is useful for us. So like we have 7 days as quite useful as part of the data set which we had over here, but it's to keep it quite less is not good. So that's why we can see over here after 3 days or 4 days, it's the accuracy remains quite same. Yeah, so that's what we had in as part of this paper. So we developed Precog, which is relevant for the cloud-based infrastructure where the particular developer or administrator doesn't have a knowledge of the applications running on the system. And we saw that Precog is able to achieve an F1 score of 0.85 with less than half a second of prediction time. So that's quite good. And last, the third point is it's scalable to thousands of virtual machines. As we saw in the scalability aspect, that we try to scale it up, so it's quite good. And lastly, although the precog depends on some parameters, but we saw that beyond a certain value, it is insensitive towards the min R square score and the critical time. So yeah, so that's the conclusion, and we want to extend this in the future towards the serverless computing, where the functions use some memory, and in the next information, the different functions use some memory, and they can lead towards the memory leaks in the future. And we want to extend this precog apart from memory to some other matrices like disk consumption and the cost budget, and to use some other metrics like CPU, network, and storage for enhancing the accuracy performance of our algorithm. Yeah, so thank you for listening to me. And yeah, if you have any questions, please reach out to me and send us an email. Yeah.